Hi, welcome to today's daily Leetcode challenge. Today I'll be solving question 380, insert, delete, get random, all at 01, so constant runtime. So the medium level question goes as follows: implement a random set class. Randomized set initializes the randomized set object, that's the constructor. Insert returns a boolean and takes in a value, inserts an item into the set if not present, returns true if that item was not present, false otherwise. Remove returns a bool and takes in a value of type int, removes an item from the set if present, returns true if item was present, false otherwise. And finally int or get random that returns an int, returns a random element from the current set of elements, and it's guaranteed that when being called, at least one element is present. Each element must have the same probability of being returned. That's just the nature of the implementation of random, but you must implement a function of a class such that each function works on average of constant time complexity. So this is the real kicker, because realistically, a set in Python would work for constant time for everything except for get random. Why? Well, because in order to get random from a set, you need the ability to choose between a range of values. And in Python, you would have to first convert that set into a list in order to do that, because a list has a property of length and it has the property of being able to access each one of those values by index, whereas set, you can't do that. Set, you can only either add a hashed value or remove a hashed value if present. And yes, in Python, sets are implemented as lists, so we could actually probably just do this, self s set, and then if val not in, let's say val in self s, then return false. Otherwise, self s add val and return true. So I'm basically just want to show that it is possible to implement this as a regular set, but it's not going to be ideal. Return false, and then self s remove val return true. And in here, let's import random, and then here we could theoretically have, let's say L is equal to len of self s, and then have return a random choice. Oh, we don't even need this. Choice of a list of self s. And this probably will work. However, this operation here is not going to be constant time. This operation will be dependent on the size of s. Why? Well, because realistically, and each time you call it, a set is then spread into another data structure, which requires every element to be called on inside of the self set and turned into a list. So unfortunately, that option is out of the, well, it's not possible. What else can we do? Well, let's see. What is the property of a, so let me just give a hint, I guess. We do want eventually to just return our values like this, right? We want to have a list of values that is constantly updated with the correct values that have been inserted or removed. But the issue here is that if we wanted to remove a specific value from that list, we would first need to find it. And finding it is what caused the issue in using a list in the first place, right? Finding a value in the list requires O of n time complexity. However, finding a value in a set, or whether that value is present there or not, is constant. So why not use the combination of those two sort of properties of finding something in constant time and also having values live in those values, a dictionary. So let's see, self values is going to be our list, and then self, what is this, val to indx is, or x's is going to be the dictionary. Now, what am I going to try to attempt to do is have values list constantly represent which values have been inserted or removed, and then I'm going to have the indices dictionary represent all of the values that are currently in the list, as well as the indices of where those things are present. That would allow me in constant time to figure out where that value is in the values and remove it in constant time. So so far everything's going to be pretty identical, with the exception of, let's see, is there a way to, I can just check if value is in the keys of indx. So indx's keys, if value is already there, then remove, or then return true. Then we need to return a true here, and between that we need to values append val. It doesn't matter where it's going to live, it just matters that the index of that value is represented correctly in the indices dictionary. Self indx's at at value is going to be equal to length of self values. That should be it. So in order to insert an element, we first find out its index, its soon-to-be index, which before insertion is just going to be the length of values itself. We add that pair value to index into our dictionary, and we append into that index our value and return true. That's it. Now for the removal is going to be a bit more complicated. We have to empty out two structures. One is going to be the list of values, and the other one is going to be the dictionary. And let's see, how are we going to do that? Well, the naive approach would be to say, let's see, val indx is going to be the index that we get from this guy. We know that by looking at value. And what else do we know? Well, is that it? Do we just have to say list self values pop val indx? Ideally, yes, and return true. However, what's going to happen here is once I pop, oh, and I forgot to also delete the pair from that key value pair. The issue with that is once I pop an element from somewhere in the middle of an array, it's actually going to mess up all of my other indices to value to indices pairs that I've stored in my index. Why? Well, because if I have, let's say, a list of 10, and I remove the third element, well, the indices of all of the other 7 elements in that list are going to be shifted by 1. And that would require me to update all of them in the self indices dictionary. I don't want to do that, so let's do a clever trick, and let's just simply, instead of popping that element from the list, I'm going to replace it with the last element from the list. Replacing it with the last element from the list will require me to just update one more value to index pair in the indices dictionary that represents my the location of that last value. So how's that going to work? Val index is going to be my value, right? And then I want to say I want to have my last value here. My last value is just going to be values -1 from the back. Okay, now what I have to do is update my my last value with the value index that I am replacing it with, right? So self indexes of last val is now going to be a new index, the index that I am removing anyway. And self what else is values at a index is now going to be my last value. And so I have, so what I just did was I had the two structures, the indices and the values, and starting off with the list, I take away the last element from that list and put it somewhere into the middle where the value used to live, and I update its index, its last value index with its last value with the index that I just replaced it with, so val index. Well, at that point, all that's left for me to do is to delete the self index's value entirely, and I can also pop the let's say self values pop the last element, because it now lives somewhere in the middle where value used to live, and that's it. So now this operation goes in O1 constant time. Self, I want the index's keys. This is just gives me a set of all the keys. It's constant time. What did I do here? Indexes. Oops. Okay. That seems to work, and hopefully no issues here. Great. And this goes around 96th percentile, so I'm not gonna go bother to check what better solutions there are. This this probably is in line with everything else, so there we go. On that, thanks for watching. Use this wherever you want. This is definitely the most efficient and the most elegant way to solve this problem. On that, thanks for watching. Please like and subscribe, and I will see you tomorrow. Bye.